This is part 2 of 7.2, which is total internal reflection. And the reason why I did 2 parts to this is because it's a really, refraction is a really big area, but it's got some weird consequences where refraction can actually start to make a reflection on the inside of a dense medium when a light ray is going from a more dense medium to a less dense medium. And a consequence of refraction as well is that when light hits from a less dense medium, a light ray hits a surface to a more dense medium, the refracted line and the reflected line start to get polarized to each other too. So when the light reflects off the surface, it becomes polarized to the refracted ray. So it's kind of really neat. So there's some cool consequences to refraction. I want to revisit it and specifically talk about polarization and total internal reflection. Okay? So if you haven't read the chapter in Coletta, please do so. It's chapter 23, but also I would probably start reading chapter 24 on lenses and spherical mirrors, as well as like the eye. I think they have some really great things about how microscopes work, how does the eye work, and also telescopes too. So cool. Okay, well, have you ever been underwater and you kind of look up at the surface of the water and you actually see the bottom of the pool? So you're underwater, you look up at the surface of the water, which is right here, and you actually see the bottom of the pool. Okay, so I thought of this and I drew this horrible drawing. Don't judge me. Anyways, so I have a fish, and what does the fishy see? Well, the fishy will actually see the person on the surface, okay, but kind of flipped, right? And so what's happening is that the light ray from the person is actually hitting the surface. The light ray in the water hits the surface, and it actually does not leave and refract out at a certain angle, and actually will totally, all of it will actually reflect off the surface back into the fishy's eyes. So this happens when it's going from a more dense medium to a less dense medium. There's an angle at which this will happen, and it's called a critical angle. And this is called total internal reflection. Okay? So what is happening? Well, you've seen there's 2 types of things that's happening. And you saw that in the PHET simulation, also the lab, where I'm going to mark up the document, go to comments, put that back to where it is. And now I can actually draw. So when an incident light ray comes in, part of that light ray will reflect off the surface. And I think we saw with air and water, we saw something like 8% of the light gets reflected off the surface, and that about 92% is refracted in, right? Well, sometimes what happens is when it hits a critical angle, the incident light ray, if it's leaving the water, some of it, at a certain angle, all of it will actually bend back in. And some of it might leave, might bend too, and that's called the Brewster's angle. And anyways, we'll talk. We'll worry about that later. But so this, at certain angles, that reflected right ray will actually be polarized too. Okay, and that's at the Brewster's angle. Well, here we go. Let's talk about total internal reflection. So as I mentioned before, there is a critical angle, or there's an angle that will happen where light does not emerge. So from leaving a more dense medium into a less dense medium. So here we go. We have a light ray moving up along the normal. So it's a slower light ray, and then it's going to speed up into the less dense medium, right? And then here we see it normally refracting, and it's going to be refracting away from the normal and speeding up. But then there's there's a certain thing that happens right here, where at a specific angle, and I believe it was 42 or 43 degrees, where light ray along that normal will actually bounce off the surface, and actually all of it will bounce back into the water. And you could see that reflect right here. So here we go. We have a light ray leaving, and then what happens is you could see part of it is traveling along the surface, just like in here. Okay, but all of it is actually bending back into the water. Okay, and so that's what that critical angle is happening at. Okay, and how you calculate that critical angle is you take the sine of the you take the sine of the less dense medium, take the sine of the index of refraction of the less dense medium divided by the index of refraction of the more dense medium. Here, N2 is the water right here, is the air, and N1 is the water. Okay, and you could test this out at the bending of light lab and just check out those different angles, right? Well, we use total internal reflection in prisms, right? So if you have binoculars, what's happening is a light ray is coming in to the end of the binoculars. It hits part of the prism, okay? It totally internally reflects off the back of that part, does it again, and then exits along the normal, and then does that same thing. It totally internally reflects off the back, does it again, and then goes back in. So we're actually using prisms to redirect the light rays into binoculars. And so these are called Porro prisms, right? And it's two prisms angled at such a way where they're leaving one at the normal and entering the other one at the normal, and then totally internally reflecting. So these are cut. So this angle right here is cut at that whatever that density is at that total that critical angle. Okay. And this is also what's happening when you see a diamond, right? Diamonds are cut at those specific angles so that light rays coming in is totally internally reflecting. And the cool thing is it's also dispersion that's happening when it's leaving. And so that's why you see white light coming in. It's bouncing off the back here. And then when it leaves, there's a little of what we're going to talk about next one. It's called dispersion, where that white light ray starts to get broken up into its different colors of Roy G. Biv, right? And so that's why you see light sparkling. We already talked about this, but this is also what happens when we have fiber optics. So we had if you've ever, I think our government spent a couple $1 million in investing in putting fiber optic cabling in between the United States and Europe, right? So that high energy speeds will actually travel faster, and more information can be carried through fiber optics. And how fiber optics work is by that total internal reflection angle. So no matter what angle that you're bending this at, this fiber, this kind of plastic fiber optic material, it's going to bounce back into itself. It's not going to refract out. So all of that light coming in is actually going to be exiting. And the great thing is, since these are bendy, you could bend them and twist them around objects. It's really great. And so what you have is you have light, which can also be a lot of information like internet and things like that. You could transfer a lot more information through fiber optic cabling, right? And no loss of energy coming out. Where if you have a signal of metal, the difference is if you have coaxial cables like we have in our house and through regular internet, well, you send a voltage along something, and that voltage, that current, will start heating up that that piece of wire, right? Well, that wire is now kind of losing information in a way. You could kind of see it like that. So part of that energy going in is actually being lost due to heat. Well, that doesn't happen with fiber optic cabling. So it's a lot more efficient use of our technology. The other consequence of refraction is that light gets polarized, right? So if you have a light ray coming in, and it'll be polarized along the X and Y direction, you know, the electric and magnetic, right? So for example, but it's actually polarized in a lot of different angles, white light is. Well, when it comes in and it hits the surface, it's going to reflect off. Well, there's an angle at which this light ray comes in and gets bounced off, and the light ray gets totally polarized when the reflected light ray gets completely polarized to the other one. So what I mean by that is this: if you have a light ray that has components of up and down, so it's polarized vertically, right? Well, you could have another part of that. So this is the y-axis I'm drawing. The y-axis I'm drawing. So this is polarized vertically. Well, you could have part of that light ray also polarized along the z-axis, right? Which I'll use as red. So the z-axis is polarized red. So I'm going to use z-axis as red. So that light ray is coming in and out of the page, right? So the black light ray is up and down. The red light ray is in and out, right? Well, if you have something that comes in along one of these angles, and you have a filter that only allows light to come in polarized up or down, right? So you put two slits in this. That's vertical slits. Well, it's only going to allow the black light ray through. The red light ray is going to actually come in, and it's actually going to hit and get stopped right here. But the black light ray is going to allow it to come through. And that's how you could make light polarized, right? Well, that's what's kind of happening with the water. You have this light ray coming in to the surface, and when it hits, in this case, which is the antithesis of our example, the vertical light ray is actually being kind of filtered out when it hits. And the red light ray is the only one that continues on. So that's what polarization is. If you have, so that's what's kind of happening at those angles. And so there's an intensity that's associated with it, right? If you have something that has a full spectrum of light at all angles coming in, and if you have something that polarizes and only allows a certain bit of light through along a certain angle, phi, well, that this light coming through is the only one that survives, right? I mean, that light ray that comes through is the only one that survives. Okay? So that's what's kind of happening. And that Brewster's angle, by the way, is tangent of theta, so theta p is that polarization angle. That's the Brewster's angle. It's tangent of the Brewster's angle is equal to the refracted the index of refraction for the denser over the index of refraction for the less index of refraction. Okay? So that's what's happening at that. That's what's kind of different. So some of you have also probably thought about mirages, or if not, you probably now. How do mirages work? What's happening is, since heat is rising from a surface, and as heat is rising, the surface is really hot, so that hot air is rising. Well, hot air, as it starts to rise and cool off as it's rising, that hot air is going to be changing densities, right? The hot air is going to be very less dense, right? And the cool air is going to be more dense, right? Well, what happens is it's got a continually changing index of refraction. So what happens is the light ray actually bends, and it acts like it reflects, but it actually is continually bending, and then it bends into your eyes. So this is the original light ray from here. So you'll be able to see the actual camel right here, which is a camel right here, but you'll see also off the surface, which looks like it's almost like wet, like water. But what's really happening is that continual change in that light ray as it's starting to bend towards the normal at those different angles, and then it will then start to bend away from the normal to come back into your eyes. So your eyes again are seeing things in straight lines, so they see the objects down here, but the actual object is right here. So what's happening is the speed of that light ray is continually changing over a small period of time, right? And so as it's speeding up and then slowing back down to its original speed. So it has a speed here, and then it starts to speed up in the less dense medium, and then it starts to cool off and slow down to its original speed. So that's how it's getting into your eyes, right? And so that's how a mirage is. It's actually refraction, a continual refraction of light going through changing mediums of air, changing densities of index of refractions of air. And this is called a Huygens principle. Okay? And this is another concept of that. It's the same idea of the Huygens principle. It's just a different representation of how this is happening. Okay? So you got cool air, it starts to bend towards away from the normal in the warm air, and then it starts to bend back towards the normal into the cool air again. Okay? And so that is total internal reflection, polarization, and mirages. I hope you enjoyed this. Thank you.